Now, the first images from the world's most powerful space telescope, James Webb, have arrived. For the first time, we see something extraordinary, a distinct glow ahead of the object, directed toward the Sun. The arrival of 3I Atlas in our solar system was already remarkable, an interstellar visitor racing at tremendous speed, carrying chemical signatures unlike anything observed before. But imagine if it wasn't traveling entirely alone. Imagine that, in the dark voids of space, it crossed long before our sun's warmth reached it. 9 hidden companions lurked in its wake, small, obscure bodies silently witnessing its long interstellar journey. The possibility that the James Webb Space Telescope JWST may have glimpsed them adds tremendous intrigue. What if these 9 objects are escorting 3I ATLAS trailing behind, running alongside, sharing the same path, or locked in a subtle gravitational dance? Such a configuration would send ripples through our understanding, not only of this visitor, but of the architecture of interstellar debris, the remnants of distant star systems, and the processes that launch such relics into our cosmic neighborhood. Before we dive in, smash the like button and subscribe for more exciting space updates. From the moment 3I Atlas was discovered on July 1, 2025, by the Asteroid Terrestrial Impact Last Alert System Atlas survey in Chile, astronomers knew it was unusual. Its hyperbolic trajectory confirmed it originated from another star system. Early observations revealed a rich coma filled with carbon dioxide, water ice, carbon monoxide, and other compounds. Yet the idea of 9 discrete objects accompanying it raises profound questions about fragment survival, capture, companion formation, and the dynamics of interstellar wanderers. How did these objects become associated with 3I ATLAS? Did they form in the same parent star system as a mini-cluster of planetesimals ejected together? Or did they become bound during the long journey, perhaps captured from another system or influenced by a passing stellar encounter? If JWST or other instruments detect them through faint trails, infrared shadows, or subtle trajectory deviations in 3I ATLAS itself, it would reveal a far richer, more complex environment than a single isolated wanderer. The dynamics are captivating. 3.1. Atlas approaches the Sun at speeds far exceeding typical solar system objects. JWST's near-spec observations occurred at a heliocentric distance of about 3.3 astronomical units, where molecular data revealed an unusually high CO to Hao mixing ratio of around 8, one of the highest ever record. Did in a comet, if 9 small companions exist, they would need to share, or nearly share, the trajectory, perhaps in a trailing formation slightly offset from the main body. This implies they were likely ejected simultaneously or once loosely gravitationally bound, now carried along the same flight path through interstellar space and into our solar system. Detection could involve faint infrared signatures beside the main coma, or subtle distortions in the dust and gas envelope. Small bodies in deep space are extremely faint, making any detection challenging. JWST's unparalleled infrared sensitivity excels at spotting gas species, dust features, and comets at great distances, but identifying 9 faint objects demands meticulous image analysis, background subtraction, and recognition of bodies moving in perfect concert with the primary one. If confirmed, next steps would include determining their sizes, compositions, mutual separations, any orbital relationships, and relative velocities. The presence of 9 companions would carry strong implications for how interstellar objects ISOs are ejected and what they transport. Until now, only 2 interstellar objects were confirmed. 1I, Oumuamua in 2017, and 2I, Borisov in 2019. 3.1. ATLAS is just the third. Discovering companions would suggest these objects sometimes travel in small groups rather than as solitary wanderers. A parent star's debris disk or planetary system might eject material in clusters, informing models of planet simul-scattering, ejection dynamics, and how material from one star system seeds another's region. Compositionally, 3. ETLAS's CO-rich nucleus suggests formation under conditions different from typical solar system comets, perhaps near a CO ice line or after prolonged high radiation exposure. If companions share this, we'd gain 9 additional samples from that alien environment, each providing a unique window into the parent system's chemistry and evolution. This elevates the discovery from one specimen to a miniature sample set. Do all 9 share identical composition, or show variations in volatile content, dust-to-gas ratios, or radiation processing? Comparing them could refine our picture of the parent system's conditions, ejection event, and galactic journey. Stability over long periods raises questions too. Without strong mutual gravity, small objects might drift apart. Their continued association suggests either a relatively recent ejection in cosmic terms or unexpected stability from shared velocity vectors and minimal perturbations. Entering our solar system exposes them to solar gravity, radiation pressure, solar wind, and gravitational interactions, potentially causing separation, fragmentation, or dispersal. If they stay close, it narrows the ejection to entry timeline or indicates interstellar travel preserved there. Proximity, observationally. Detecting 9 small bodies would push instrumentation limits, JWST's optics and infrared tools. Enable faint thermal signatures and compositional analysis at vast distances. Claims would require multiple observation epochs, high signal-to-noise images, precise background subtraction, and proper motion tracking aligned with the primary comet, distinguishing them from background asteroids, faint stars. All noise demands excellent calibration and confirmation. Follow up with ground-based telescopes. Radar. All other space assets would track trajectories and relative positions. Theoretically, this suggests the parent system ejected a group of planetesimals, perhaps during a close planetary encounter, chaotic early evolution, a giant molecular cloud passage, or dense stellar interaction, supporting the idea that interstellar comets may arrive in families. Our small ESO catalog might need to account for grouped rivals. Altering statistical detection models, heterogeneity among the 9, different surfaces, volatiles, processing histories, would offer a richer dataset. 9 mini-analogs instead of 1. Spectroscopy could compare infrared signatures. Dust emissions, outgassing, reflectance, pristine. Less processed companions would make this a treasure trove, a miniature sample return mission. Without launching a spacecraft, implications for solar system science are vast. Extrasolar material entering clusters means fragments from other systems may arrive more often than thought. Previous visitors might have had undetected companions. We lacked sensitivity before. This reshapes ESO searches. Look for faint trails or trailing bodies along shared trajectories. Compositions preserve signatures of unfamiliar star-forming regions, isotopic ratios, ice phases, dust, volatiles feeding models of planet formation, evolution, galactic exchange. As the cluster pauses, solar heating drives sublimation, surface changes, Comey, tails. 3.1. ETLAS already shows activity from CO and volatiles. Smaller companions might differ, inert, faint Comey, or full fragmentation, providing a natural experiment in interstellar body responses to new stellar environments. Broader view, our system isn't isolated but open to visitors, perhaps in streams from ejecting star systems. 3.1. ETLAS's rival possibly with 9 others hints we may cross such a stream, suggesting periodic crossings by unseen debris families. Planetary defense. Group rivals raise monitoring needs. Earlier, deeper searches for faint trails with known ISOs, targeted studies or missions become possible. One full close-up. Others comparative. Multiple bodies from one ejection test origin hypotheses robustly. Shared CEO. Ratios, variations, isotopic. Dust differences indicating heterogeneity in ejected parcels. Companions affect trajectory modeling. Mapping divergences reveals binding strength. Dispersion. Tidal influences. Some may separate, become free drifters. Tracking evolves an interstellar cluster entering a star system. Unprecedented. Pristine samples among them. Less active, smaller, less heated. Preserve frozen records of formation chemistry. Processing. JWST or future tools target infrared spectroscopy. Dust, tails, composition, refining origin insights. Perhaps see O-rich zones or unique radiation histories. Philosophically, clusters mean our system is penetrated by small fleets from elsewhere, fostering a cosmic perspective of galactic matter exchange over eons. E.g. so is a messenger from another star, time, place. Practically, confirmation galvanizes rapid study, limited window before solar heating obscures or fragments them. Campaigns map positions, motion, spectroscopy, imaging, light curves, tail evolution, mobilizing infrared, UV, visible, dust, gas instruments. Data expands extrasolar catalog tenfold. Theoretically, cluster isos demand multi-object ejection in models, resonances, scattering, binaries reconsidered, detection probabilities shift to bursts, streams, wide-field infrared, deep, high-cadence surveys for trailing objects, end states, post-passage. Perturbations alter trajectories, likely exit interstellar, but interactions strip dust, sublime it. Fragment, rare capture possible, 9 increase interaction chances, dust trails, wind effects. Ejector. In summary, JWST potentially detecting 9 hidden objects escorting 3I. ETLAS is more than intrigue, a window into richer interstellar processes. It suggests crossings aren't solitary but accompanied. It rethinks detection. Interpretation of composition, trajectories. Galactic material flow. Confirmation multiplies opportunities, multiple records of distant. Environments. Vantage points on formation, evolution beyond our backyard. Not one specimen, an entire entourage. Passing through our cosmic neighborhood. If JWST truly captured this, it redefines not just one event, but humanity's view of matter movement between stars. Each faint companion fragments a greater mechanism binding the galaxy in shared exchange. Their coordinated rival marks first evidence interstellar debris travels in formations, challenging random perceptions, revealing systematic celestial choreography across light years. JWST's technical feat, precision discerning dim echoes in deep space background, faint thermal variations, tiny glowing dots in lockstep, too consistent for chance. It highlights space-based infrared astronomy's power to uncover invisible structures, astrophysicists would model cluster survival through radiation, micro-collisions, extremes requiring stabilizing mechanisms, magnetic interactions, shared outgassing, synchronized velocities, hinting unexplored principles like interstellar co-migration. Miniature floatiers traversing the galaxy. It implies our system may have been brushed by such groupings many times, unnoticed until now. If you enjoyed this deep dive, give it a like, subscribe to the channel, and drop your thoughts in the comments. What do you make of JWST potentially discovering hidden objects near 3I ETLAS? We want to hear from you. Thank you for watching. See you next time. Keep looking up. This should run approximately 10 to 12 minutes at natural speaking pace. Add pauses for emphasis, visuals, JWST images, animations of companions, trajectories, and background music to amp the mystery. If you want it shorter, longer, or with more, less speculation, just say,